Right now, as you watch this, the universe is getting bigger. Not just bigger, it's expanding faster. Every second, the space between galaxies grows, and tomorrow it will grow faster than it does today. Last time, we talked about dark matter, the invisible mass that holds galaxies together, that keeps them from flying apart. Well, there's something doing the exact opposite. A force that works against gravity. A force that is pushing everything in the universe apart and winning. It makes up roughly 68% of all the energy in the cosmos. That's more than dark matter, more than everything else combined. And we understand it even less. To understand how badly this discovery shook everyone, you have to go back to what everyone believed. For the entire 20th century, the picture was simple. There was a Big Bang. The universe started expanding. And gravity, the only force that matters on cosmic scales, should be slowing that expansion down. The same way a ball thrown straight up slows as Earth pulls it back. There was only one open question. Was there enough gravity to one day stop the expansion and pull everything back together into a reverse Big Bang, a big crunch? Or had the universe expanded too fast so that it would keep growing forever, slower and slower, approaching a stop but never quite reaching it? Notice something. In both versions, the expansion slows down. That part wasn't up for debate. It wasn't a hypothesis. It was just obvious. Gravity attracts. Gravity slows things down. End of story. All that was left was to measure how much it was slowing. And that seemed like a tidy, almost boring job for astronomers. In the late 1990s, two independent teams took it on. Their method was beautiful. To measure how the expansion rate had changed over time, you have to look into the past. And in astronomy, looking far away means looking back in time, because the light from distant objects has been traveling toward us for billions of years. All they needed was a reliable way to measure enormous distances. And there is one. It's called a type I supernova. It's a specific kind of stellar explosion. Its key property is that all of these explosions happen at almost the same mass, and so they shine with almost the same true brightness. It's a standard candle. If you know how bright something truly is, and you can see how dim it appears, you can calculate exactly how far away it is. Both teams collected these supernovae from all across the sky. They expected to see the signature of slowing down. They were only arguing about how strong it would be. It was 1998, and they got an answer they didn't believe at first themselves. The distant supernovae were fainter than they should have been. Fainter means farther. Farther than they had any right to be if the universe were slowing down. These galaxies had moved away from us by more than any model of a decelerating cosmos predicted. There was only one way to explain it. The expansion of the universe is not slowing down. It's speeding up. Stop and sit with what that means. Something is overpowering gravity. Gravity is still pulling everything together, and it's losing anyway. Some force is pushing space apart, and with every passing moment, it's pushing harder. Both teams, working independently, blind to each other's results, arrived at the same impossible conclusion. That's why it was believed. In 2011, the discovery won the Nobel Prize in physics. But a Nobel Prize doesn't explain what it is. We gave it a name, and that's all. Dark energy. Here's what makes it genuinely strange. Take any ordinary form of energy or matter. Stretch out the space it sits in, and it thins out, gets more dilute. Inflate a box of gas, and the density of the gas drops. That's how everything we know behaves. Dark energy does not behave that way. The more space there is, the more dark energy there is. Its density doesn't fall. Every cubic meter of empty vacuum, it seems, carries a fixed amount of this pushing energy. And because the expansion creates new space, it creates new dark energy right along with it. That's the loop that makes this accelerate. More space means more dark energy, means a stronger push means even more space. The universe is feeding its own acceleration. It appears to be the energy of emptiness itself. a property of nothing. Now you might be wondering, what if this is a mistake again? One type of explosion, one measurement? Fair. So let's look at what else we have. First, the supernovae themselves. That 1998 discovery, now confirmed with far more supernovae, reaching far deeper into space. Second, the echo of the Big Bang. The universe is filled with faint microwave radiation left over from its earliest moments. The pattern in that radiation lets us measure the overall geometry of the cosmos, and it turns out to be flat. And to be flat, the universe has to contain a specific total amount of energy. Add up all the normal matter and all the dark matter, and we come up short by almost 70%. Something is missing, and that something matches the amount of dark energy exactly. Third, the large-scale structure of a universe. The way galaxies have gathered over time into filaments and clusters depends on a tug-of-war between two forces: gravity pulling in and dark energy pushing out. The picture we observe only adds up when we include dark energy. 3 independent lines of evidence. Different methods, different data. The same answer. Something is pushing the universe apart, and there's a lot of it. So what is it? This is where the most embarrassing part of the whole story begins. The leading candidate was proposed almost 100 years ago by Einstein himself. When he built the equations of general relativity, he added a small term, the cosmological constant, a kind of energy built into space, the same everywhere. Later, once we learned the universe was expanding, Einstein removed that term and, as the legend goes, called it his greatest blunder. And in 1998, it turned out that term was exactly what we needed. A constant energy of empty space is precisely what describes dark energy. You'd think that's the end of the story. It isn't, because when quantum physics tries to calculate how much energy should be in the empty vacuum, it produces an answer. And that answer is larger than what we observe by a factor of 10 to the 120th power. To be clear, this is not "we were a little off." That's a 1 followed by 120 zeros. It is the worst quantitative prediction in the history of science. Theory and observation disagree more violently than on anything else physics has ever tried to calculate. So yes, we have a candidate, and along with it, a gaping hole at the very center of our understanding. There are other ideas. Maybe dark energy isn't a constant, but a field that slowly changes over time. That version is called quintessence. If it's right, the pushing force could have been different in the past and could become different in the future. Or maybe, just like with dark matter, there's no new substance at all. Maybe our theory of gravity is simply incomplete on the largest scales, and we're mistaking a gap in our own equations for a mysterious energy. Right now, we can't say for sure. Entire observatories are being built at this very moment for one question: does dark energy stay constant, or is it quietly changing? The fate of everything depends on the answer, because dark energy isn't just a puzzle about the present. It's the thing that decides how all of this ends. If the acceleration continues the way it's going now, the future looks grim. Over time, distant galaxies will recede from us faster and faster, until their speed of retreat exceeds the speed of light. At that point, their light will never reach us again. One by one, galaxies will wink out of the sky, not exploding, just slipping past the edge of the visible. Stars will live out their lives and go dark. No new ones will form. Everything will cool toward absolute zero. Physicists call this the heat death of the universe, the big freeze. Not a bang, but a slow, quiet sinking into darkness and cold. And there's a sharper scenario. If dark energy isn't constant but grows stronger over time, it will eventually overpower not just the gravity between galaxies. It will tear apart the galaxies themselves, then star systems, then planets, then atoms, and in the final instant, space-time itself. That ending is called the Big Rip. Which scenario is true depends on exactly what we don't yet know, whether dark energy is constant or not. Here is where we stand. Dark matter holds everything together. Dark energy pulls everything apart. Together, they make up about 95% of the universe. And we don't truly understand either one. Everything you have ever seen, every star, planet, galaxy, every atom in your body, is the remaining 5%. A thin, glowing film over two enormous mysteries. And here's a thought to leave you with. Right now, we live in a special window of cosmic history. The sky is still full of other galaxies. We can still see them, study them, measure them, which is the only reason we ever learned about dark energy at all. But the acceleration continues. In 1 trillion years, those galaxies will be gone past the horizon. Future beings, whoever they are, will look up and see only emptiness. They won't even have the clues to guess that the universe was once full of light. We arrived just in time to watch it all disappear. If you found this interesting, the next video is about exactly how this long darkness ends. The heat death of a universe. What happens to the last star, the last black hole, and the final flicker of energy on timescales beyond anything we can even imagine. Subscribe so you don't miss it.